Hello everyone, I'm Kaiyu from Northwestern University. Our work is about discovering emergency call pitfalls for cellular networks with formal methods. The cellular emergency call system consists of three major parts: user equipment, UE, carriers, and public safety answer points, PSAP. It is an important system. 240 million 911 calls are made each year, and 80% of them are from cellular networks. However, no previous work thoroughly analyzed its correctness or found its vulnerabilities. Our goal is to apply formal methods to systematically discover the availability and security issues in this system and explain their underlying mechanisms. Formal methods have been used in cellular network research and have achieved success in crypto-related protocols, such as AKA protocols. But it is still challenging to apply formal methods to general cellular network protocols for two reasons: modeling granularity and misrepresentation. There are always gaps between protocol definition, formal specification, and system implementation. To apply formal methods, human language-based protocols need to be first translated into formal models. However, there is no golden rule for the granularity of modeling. Cross-grade specification needs to force positive counterexamples due to over-abstraction. Fine-grade specification requires impractical efforts. On the other hand, protocols have many flexibility options which may not be used in the real-world systems. Therefore, models based on only protocols may not accurately represent the real-world systems. To address those two challenges, we first identify key features in the security study for cellular networks. First, the cellular network is a critical system. It is worthy to investigate and expose the security issue for the underlying causes. In this way, we can use the knowledge learned from the investigation to decide the modeling granularity. Second, instead of aimlessly searching for any potential vulnerabilities in the system, we are interested in searching for other similar issues under the same causes. Therefore, we can narrow the scope of the verification task. Third, configurations of cellular network systems can be measured on air or at the UE side. We can use the real-world configurations to augment our specification. As a result, we can get a formal model which reflects real-world systems. Based on those observations, we propose the state-assisted specification method. It has three stages. At the first stage, we use an exposed security issue as the seed of our specification. We collect related information about it, perform reasoning, and test our reasoning results. At the second stage, we use the prior knowledge learned from the first stage to guide the protocol specification, design security properties, and augment real-world configurations into the model. With such a model, the counterexamples found by the formal verification at the third stage tend to be practical in the real world. As a case study, we investigate the cellular emergency call system to demonstrate our framework. The seed was a piece of shocking news in China at 2019. It motivated us to start this research. In this news, the victim tried to dial 120, the ambulance emergency number in China, from her Meizu MX6 UE. The UE had a valid SIM card and was covered by a good signal. However, all the emergency calls failed, no matter the ones dialed from the knocked screen emergency panel or from the unknocked normal panel. She only heard a repeated dialing instruction from the UE, and the calls never got routed. From the news interview, we could collect information such as the UE model, the system information, and the detailed procedures. We perform set collection from three aspects: cellular network protocols, implementation details of UEs, and configurations of carriers. We mainly focus on the call setup protocols and emergency call related protocols. We also analyzed the source code about Android and Meizu systems to investigate the causes. The carrier's configurations were measured on air or inferred from the related documents. The reason for this case is due to the historical setting in China. In the protocol, two signalings can be used to initiate a phone call: emergency setup signaling and normal setup signaling. When a user dials a protocol-fixed emergency number, 112 or 911, the UE will initiate this call with the emergency setup signaling. Chinese carriers will respond to this signaling with a dialing instruction: dial 110 for police, 119 for fire, 120 for ambulance, and will not route this call. Instead, if a user dials a no-call emergency number, 110, 119, or 120, and the UE initiates this call with the normal setup, Chinese carriers will directly route this call to the corresponding PCF. This is due to the traditional landline system in China using ITU signaling system, which does not support the 3GPP emergency setup. This setting is compatible with the traditional system, where it also responds to the emergency setup signal to some extent. Thus, it has been used in the cellular emergency call system till today. We therefore speculate that the MX6 forcibly initiated calls with emergency setup and thus failed to be routed. We reproduced our speculation with the same UE and the same system version. Packet sniffer shows that MX6 indeed uses emergency setup to initiate these calls. We also programmed other UEs to initiate calls by emergency setup. All of them failed. These experiments confirmed our reasoning. Please check our paper for the solution of this issue and how other cell phones mitigate this problem. We continue to investigate other potential issues. Our goal is to specify our formal model for the system and find potential vulnerabilities related to this one. With the prior knowledge learned from the reasoning, we specified the formal model of the cellular emergency call system in TLA+. It has two parts, UE and the network, which are synchronized by our message channel. There are 36 configurable variables in this model. The model yields 10 billion distinct states with the max diameter of 26. We have open-sourced our formal model as well as the model checking tools and GUI utilities online. we designed two properties. The nameless property states that if a user dials a local emergency number, the call should eventually be routed to the corresponding PCF. The safety property states that any call should not be routed to a non-corresponding callee. It avoids the chance to abuse the privileges of emergency calls in the normal dial. We collected the system configurations from all major Chinese carriers and 2 major US carriers. We augmented the model with those configurations and studied the security and availability issue on the model. As a result, we found 4 failure scenarios in China that emergency call cannot be routed. We also found 2 attacks that abuse the emergency call privileges in the US. They are all validated by off-the-shelf devices and acknowledged by corresponding carriers. We will explain one failure and one attack here. In these failure scenarios, a tourist who is roaming in China has a valid SIM card, uses localized UE to avoid Meizu's case, and has a roaming subscription. However, he cannot initiate an emergency call in China by the emergency panel if his home local emergency number is different from China. This case best shows the power of formal methods. It is hard to discover without systematically studying, but it is easy to reproduce once we found it. As shown in these figures, we can easily validate this failure. The first cell phone has a valid subscription from China Mobile, but refused to dial 110, the emergency number in China, from the emergency panel. Please check our paper for detailed reasons for this case. We show the UE screen lock bypassing attack in this figure. By pushing one sophisticated message to the UE, the adversary can dial any normal number on the emergency panel of the victim's UE without unlocking the screen by password. Once again, it's easy to reproduce once we found it. In Figure A, we push a fake local emergency number 224-714 to the UE. In Figure B, the UE identifies the normal number 224-714 as an emergency number, and we can dial this normal number on the emergency panel without unlocking the UE. To the best of our knowledge, this is the first attack that can bypass the UE password to make phone calls. This attack has the similar effects as the well-known caller ID spoof attack, but it can bypass the state-of-the-art defense mechanisms because the phone number is not forged. We devised a technical solution in 4 steps to address all the emergency call system issues. We show the correct list of our solution in the paper. We also argue that signal network features, which have high social impacts but make no profits, such as emergency calls, shall be seriously considered and clearly defined by protocol designers. It is the social responsibility of the protocol committee to the public. In conclusion, we propose the set-assisted specification method to apply formal methods to cellular networks. We specified a formal model and conducted the first research to study the cellular emergency call system. We found 4 failure scenarios and 2 attacks in the system, and we devised a solution to address them. Thank you.